Okay, let's talk about the Maxwell Boltzmann curve, but while we talk about the Maxwell Boltzmann curve, we've got two different things to consider. We must consider that curve, and we must also consider this progressive reaction curve. Now remember, for any reaction to occur, we always start out with a certain amount of energy in our reactants. It depends on the nature of the bonds in the reactants, how much energy the reactants have. And the same thing with the products. All reactions have a certain amount of energy in the products, and that energy is tied up in the bonds, okay? But for any reaction to occur, this is obviously an exothermic reaction, but whether the reaction is exothermic or endothermic, every reaction starts out with the reactants at a certain amount of energy, and then energy needs to be added. And I sometimes tell you about how it's like pushing a rock up a hill. So you get some energy, you push the rock up a hill, and then boom, the reaction carries on forward. So equivalent to pushing the rock up the hill is what's called the activation energy. So you might have noticed that some reactions go faster when you heat them or stuff like that. And you've got the same nature of bonds in the particles, but the reaction goes faster when you heat them. And that's got to do with this activation energy and how you get the activation energy. So this curve is related to the Maxwell Boltzmann curve, okay? Think about this. You remember temperature, the average kinetic energy of a substance is proportional to its temperature because the particles are moving faster and there are more collisions, okay? And remember now, collision theory is how reactions occur. Like for instance, if you have a sample of gas like this, the particles are banging into each other all the time. This is what causes gas pressure, the particles banging into each other in the sides of the container. Now these collisions are assumed to be totally elastic. Remember gas laws from grade 11. So when the particles bang into each other, sometimes one starts moving faster and one starts moving slower. So if we come back to our temperature definition, temperature says it is related to the average kinetic energy of the particles. So if you were to put your finger into this gas at any time and you could, detect individual gas particles, the gas particle would have a certain amount of energy. And I don't know if you just saw that one gas particle suddenly stopped after it hit something or went a lot slower. Some of the particles will be going very fast, some of them will be going very slow, but they will all have an average speed. And this is what is plotted on the Maxwell Boltzmann curve, okay? So on the Maxwell Boltzmann curve, if you could count how many particles, there are no particles with no energy. But if you could count all the particles and measure how fast they're going, the majority of them are going to fall over here where the peak of the graph is. And this peak of the graph will be their average kinetic energy, or basically their temperature, because temperature is a measure of the average kinetic energy of the particles. So if most of the particles have this amount of energy, you need to consider what is the activation energy for your reaction, okay? And the activation energy usually lies to the right of the energy distribution, or that's how they show it. So for instance, like rusting does not happen immediately, but if I throw vinegar on bicarbonate of soda, that happens immediately. So if you were to, for instance, compare those reactions, the activation energy for the bicarb and vinegar reaction will probably be somewhere around here, like nearly all the particles can react, because nearly all the particles have got enough energy to push the rock up the hill of activation energy on the other graph. But if you look at rusting, the line is probably much further to the tail end of the graph. So at any given time, there are a few particles rusting, but not actually a whole heck of a lot of them. So let's go back to this graph over here. Okay, look at this graph here, and now look at this energy hill. This amount of energy, because this is an energy axis. So if you take the energy of the reactants and the activation energy, you will get amount of energy in kilojoules that needs to be added to the reactants per mole of reactants to get the reaction to occur. So if you come back here to this graph, and this is a measure of kinetic energy, and here is 0, 10, 20, 30, 40, whatever. If on the other graph you read off 50 kilojoules per mole, you come to this graph and you drop a line. Where is 50 kilojoules per mole? And then you have a look. Oh, look, most of my particles have got that much kinetic energy, then the reaction will occur. So look at it a bit bigger. Here's the curve, okay? It's the range of energy of the particles. So if here is my activation energy that I read off the other graph by taking the energy for the activated complex minus the energy inherent in the reactant particles, you'll get this activation energy. The area under the curve tells you exactly how many particles there are, because there's this many on this axis with this much kinetic energy, this many with that much. You know, if you find the area under a curve, it's going to give you the number of particles. So this blue energy is the number of particles with activation energy or more, and that will tell you, will the reaction happen? If the activation energy lies off the graph, you're never ever going to get the reaction to happen. Your particles don't have enough kinetic energy. So if you then heat your sample, can you see this blue line is temperature 1 and the red line is temperature 2? If you heat a sample of gas, all the particles will have a higher average kinetic energy. So this graph, the peak, which was the temperature, because remember the temperature and the energy are like directly comparable, okay? Here at temperature 1 is the peak. At temperature 2, the peak is moved off to the right. And you can see the graph has widened and lowered. So the whole graph has basically shifted to the right, but the peak has dropped. If we still come and think about that original curve with the activation energy, how much energy you must put in to get the reaction to occur, that doesn't change because the nature of the reactants and the products hasn't changed. But all of a sudden, in our sample, can you see the area under the red curve is a lot bigger than the area under the blue curve? So sample at a higher temperature all of a sudden has more particles that can undergo the reaction. Okay, so if you have a look here, if the temperature of the reaction system increases, the rate of reaction increases because there are more effective collisions. So that's what's happening here. More particles have this activation energy or greater, because the curve at 20 degrees looks like this blue curve, and a curve at 30 degrees looks like this red curve, and the area under the curve at activation energy or greater is much, much bigger when the curve is shifted to the right. So just look quickly again. Here's now a catalyzed reaction. So here's my reaction progress graph, this one on the right here. And here's my energy of the reactants, which depends on the nature of the bonds and what kind of bonds there are. Here's my energy of the products, depends on their bonds. And then here is the hill you must push them up to get the reaction to start. And in an uncatalyzed reaction, it's a really, really big hill. In a catalyzed reaction, it is a small hill. So what happens here is, if we read these values, this potential energy value off the graph, and we go relate it back to our sample, this activation energy without the catalyst is very high. Imagine 0, 10, 20, 30, 40, 50. See, the green line for activation energy without a catalyst is very high. But the reactivation energy with a catalyst, which on this graph is this little red line, this is a very small value of the axis. So you come here 0, 10, 20, 30, 40, and it'll be the small value. So now can you see, if you shade the area under the graph, there's way more particles with the activation energy or more if you add a catalyst. So the reaction goes ahead at the same temperature, but it goes forward much faster because the area under the curve is greater. Then the last thing that you can look at with this is what happens with concentration. Now check these two graphs. The peak is in the same place. The peak is related to the average kinetic energy of the particles. So because the peak is in the same place, the temperature is in the same place. But check how much bigger this other curve is. So the bigger curve gives you an increased concentration. There's just in totality more particles. Okay, but they are at the same temperature because the temperature peak is in the same place. Now we've not changed the activation energy because we haven't changed what particles we have. So here comes the line for the activation energy, and under the small curve, the area under the curve is pale blue, and under the larger increased concentration curve, it's a darker blue. So this reaction will go ahead more happily because there are more particles with the activation energy or greater. So this is what the increased concentration curve looks like. The peak is in the same place because the temperature is in the same place, but the entire curve is in general bigger. Okay, so this is increased concentration. This is the curve where you read the activation energy off this reaction progress graph, and then you plot the activation energy against the energy of the particles. Okay, and then finally there's the other one with the temperature shift. So at temperature 1, the peak here is a low temperature because the average energy is low. Here is a high temperature because the average energy is high. And then for activation energy, once again you look at the area under the curve because that gives you the number of particles with that much energy or more energy. So I hope that helps with the Maxwell Boltzmann curve.